We have resurrected their bones and mounted them in our great halls, colossal skeletons of stone that stand as silent monuments to a lost world. We have mapped their footprints, tracing the paths they walked across ancient floodplains. We have analyzed their teeth and their claws, deciphering the brutal mechanics of their survival. We have, in a sense, reconstructed the public lives of the dinosaurs, their wars, their hunts, their epic migrations. But there is a deeper, more fundamental aspect of their existence that has remained. For over a century, shrouded in mystery, their private lives. How did these magnificent creatures, the undisputed masters of our planet for 150 million years, create the next generation? How did a 9-10 40-foot-long Tyrannosaurus rex court a mate? What signals of fitness did a 50-ton Argentinosaurus display to another? How did a heavily armored Ankylosaurus, a living tank, covered in bony plates and wielding a tail club, even manage the physical act of mating? These are some of the most profound and challenging questions in all of paleontology. They take us beyond the bones and into the realm of behavior, a ghost that rarely fossilizes. The story of dinosaur reproduction is not a tale of clear-cut facts, but one of painstaking forensic investigation, where every clue is precious and every theory is hard-won. The central challenge is a simple, frustrating fact of fossilization. Soft tissue almost never survives the journey across deep time. Muscles, the skin, the delicate internal organs, the very machinery of life and reproduction are the first things to decay, vanishing within weeks of death. What we are left with is the durable, mineralized skeleton. But a skeleton is a silent witness. It does not record the color of a creature's feathers, the sound of its voice, or the intricate dance of its courtship rituals. To reconstruct the reproductive behavior of dinosaurs, we cannot simply dig it out of the ground. We must build it, piece by piece, using the tools of scientific inference. Our primary tool in this investigation is a powerful concept known as phylogenetic bracketing. It sounds complex, but the idea is simple and elegant. To understand a trait in an extinct animal, we look at its closest living relatives on the evolutionary tree. For dinosaurs, this creates a bracket with two crucial data points. On one side, we have the crocodilians, alligators, and crocodiles. These are archosaurs, part of the same great ruling reptile group as the dinosaurs, but their lineage branched off before the dinosaurs appeared. They represent a more ancient, conservative branch of the family. On the other side of the bracket, we have the birds. Birds are not just related to dinosaurs, they are dinosaurs. They are the direct descendants of one specific group of theropod dinosaurs. It's the only branch of the family to survive the Great Extinction 66 million years ago. They represent a living, breathing, and highly evolved data point. The logic of the bracket is this. If we see a specific trait that is present in both crocodilians and birds, it is highly probable that their last common ancestor also had that trait. And since dinosaurs are nested within that evolutionary tree, between crocodilians and birds, it is almost certain that they possess that trait as well. This method allows us to make powerful, evidence-based inferences about the unseen biology of the deep past. So, let us apply this first bracket to the most fundamental question of all. How did dinosaurs physically reproduce? Crocodilians practice internal fertilization. The male possesses a penis that is used to transfer sperm to the female. Birds, with a few exceptions like ducks and ostriches, do not have a penis. Instead, both males and females have a multi-purpose orifice called a cloaca. They reproduce via a cloacal kiss, a brief moment where they press their cloacas together to transfer sperm. What do these two seemingly different methods have in common? They both use a cloaca. The cloaca, whose name comes from the Latin word for sewer, is the all-in-one utility port of the archosaur body plan. It is the single opening for the intestinal, urinary, and reproductive tracts. Everything feces, uric acid, eggs, and sperm exits the body through this one orifice. Since both crocodilians, the ancient branch, and birds, the modern branch, possess a cloaca, it is a near certainty that non-avian dinosaurs did as well. This is our first crucial piece of anatomical reconstruction. There was no separate external genitalia visible on a dinosaur. There was a single, discrete opening beneath the base of the tail, the gateway to life. Whether male dinosaurs possessed an internal, retractable penis like a crocodile, or engaged in a cloacal kiss like most birds, is still a matter of debate. But the presence of the cloaca itself is one of the most solid inferences we can make about their soft tissue anatomy. The second slam dunk inference from our phylogenetic bracket is that dinosaurs laid eggs. Crocodilians lay amniotic eggs with leathery shells. Birds lay amniotic eggs with hard, calcified shells. The fossil record provides the ultimate confirmation. Fossilized dinosaur eggs are some of the most evocative and important traces of dinosaur behavior ever discovered. The science of studying fossil eggs is called eology, and it provides a direct window into this critical part of their life cycle. The first scientifically recognized dinosaur eggs were found not by a paleontologist, but by a Catholic priest in France in 1859. However, the most famous discovery came in 1923, when an expedition from the American Museum of Natural History, led by the intrepid explorer Roy Chapman Andrews, ventured into the Gobi Desert of Mongolia, at a site called the Flaming Cliffs. They found the first nests of dinosaur eggs still containing the fossilized remains of unhatched embryos. They belonged to a small, herbivorous dinosaur called Protoceratops. For the first time, the world could see the beginning of a dinosaur's life. Frozen in stone for 80 million years, its discovery confirmed, with hard physical evidence, what the phylogenetic bracket had predicted. Dinosaurs were oviparous, or egg-laying creatures. With these foundational pieces in place, the cloaca as the anatomical gateway and egg-laying as the method of reproduction, the investigation can begin to move into more complex and speculative territory. How did dinosaurs distinguish between male and female? This is a concept known as sexual dimorphism, where the sexes of a species exhibit different characteristics beyond their reproductive organs. In many modern birds, this is obvious. The male peacock is a riot of iridescent color, while the peahen is a study in drab camouflage. Finding evidence for sexual dimorphism in the fossil record is incredibly difficult. We cannot see color or soft tissue displays. We must look for subtle differences in the skeletons themselves. For years, paleontologists have searched for a male and female morph for various dinosaur species. Some have proposed that the females of certain species, like Tyrannosaurus rex, may have had a wider pelvic girdle to allow for the passage of large eggs, or that a specific bone in the tail, the first chevron, was shorter in females for the same reason. However, these hypotheses are highly debated. The variations seen in these bones could also be due to individual variation, age, or disease. Without a fossil of a dinosaur that died while actively laying an egg, the ultimate smoking gun, identifying the sex of a dinosaur from its skeleton alone, remains a monumental challenge. This is the landscape of our investigation. We are forensic scientists of deep time, armed with a few precious clues. The anatomy of living relatives, the stony shells of long-lost eggs, and the subtle, often ambiguous variations in the bones. From this sparse evidence, we must reconstruct the entire vibrant story of how these magnificent animals fell in love, raised families, and perpetuated their dynasty for an almost unimaginable span of time. The story begins not with the egg, but with the complex and often violent prelude to its creation, the art of courtship. Before the first egg could be laid, before the first nest could be built, a far more ancient and intricate drama had to unfold. This was the drama of courtship, the complex biological negotiation that determines who gets to pass their genes on to the next generation. For dinosaurs, as for all animals, this was the most important game they would ever play. It was a high-stakes competition of display, of ritual, and sometimes of brutal combat. Reconstructing this ephemeral behavior from the deep past is a profound challenge. But by combining clues from the fossil record with the vibrant behavior of their living relatives, we can begin to paint a surprisingly detailed picture of dinosaur romance. The fundamental purpose of courtship is twofold. First, to identify a suitable mate of the same species, and second, to assess that mate's fitness. Is this individual healthy? Is it strong? Does it possess the traits that will give our offspring the best chance of survival? Animals have evolved a staggering array of signals to answer these questions, and dinosaurs were likely no exception. Our best evidence for how they signaled to one another comes from the bizarre and wonderful structures preserved on their fossilized skulls and skeletons. The crests, horns, frills, sails, and spikes that make many dinosaurs so visually spectacular. For a long time, these structures were interpreted purely as weapons or defensive armor. The massive frill and horns of a triceratops were seen as a shield against the bite of a tyrannosaurus. The elaborate, hollow crest of a hadrosaur like Parasaurolophus was thought to be a snorkel for breathing underwater. But as our understanding of evolutionary biology grew, scientists began to reconsider these structures through the lens of sexual selection. This is the evolutionary pressure that favors traits that increase an individual's success in mating. Even if those traits are cumbersome or offer no direct survival advantage. The classic example is the peacock's tail. It's beautiful but metabolically expensive and aerodynamically disastrous structure that exists for the sole purpose of impressing a mate. Suddenly, the bizarre headgear of the dinosaurs made perfect sense. These were not just weapons, they were billboards. They were elaborate, highly visible advertisements of an individual's health, age, and genetic quality. Consider the ceratopsians, the horned dinosaurs. A large, robust, and perfectly formed set of horns on a triceratops was not just a formidable weapon. To a potential mate, it said, "I am healthy enough to grow these massive structures. I'm strong enough to wield them. I am a superior individual." To a potential rival, it sent an equally clear message of dominance. Fossil evidence strongly supports this interpretation. Paleontologists have found numerous ceratopsian skulls with puncture wounds and healed lesions on their frills, and faces that perfectly match the horns of their own species. This is the stony scar tissue of ancient courtship battles. Direct evidence of males locking horns and fighting for the right to reproduce, just as deer and elk do today. The hadrosaurs, or duck-billed dinosaurs, provide another spectacular example. These herbivores were famous for their incredible diversity of hollow, bony head crests. The long, curving tube of Parasaurolophus, the plate-like crest of Lambeosaurus, the helmet-like dome of Corythosaurus, these were not random shapes, they were species-specific. This is a classic hallmark of a feature used for social signaling. It allows an animal to quickly and easily identify a member of its own kind. But the hadrosaur crests likely did more than just look distinctive. Their hollow internal structure, with its complex network of air passages, has long suggested that they were resonating chambers used to produce sound. By creating detailed digital models of these crests and running airflow simulations through them, scientists have been able to reconstruct the likely sounds these dinosaurs made. The results suggest that each species would have produced its own unique low-frequency call. A herd of hadrosaurs would have been a vibrant, noisy place filled with the deep, resonant calls of individuals communicating, warning of danger, and most importantly, advertising for mates. The crest was a musical instrument, and the Mesozoic air was likely filled with the love songs of the dinosaurs. A male Parasaurolophus with a particularly large crest may have been able to produce a deeper, more resonant call, a clear and honest signal of his size and maturity. The evidence for visual and auditory display is compelling, but what about color? Color is one of the most important signaling tools in the modern animal kingdom, especially among birds. It is also one of the most frustratingly ephemeral traits, as pigments rarely fossilize. For decades, the color of dinosaurs was a matter of pure speculation. But in the 2010s, a revolutionary discovery changed everything. Scientists found that in exceptionally well-preserved fossils of feathered dinosaurs from China, they could identify the microscopic pigment-containing structures called melanosomes. By comparing the shape, size, and arrangement of these fossilized melanosomes to those in modern birds, they could reconstruct the original colors and patterns of these dinosaurs with a high degree of confidence. The small, four-winged theropod, Anchiornis, was revealed to have a striking black and white spangled body with a dramatic reddish-brown crest on its head. The larger Sinosauropteryx had a reddish-brown and white striped tail. These were not the drab, gray-green monsters of old illustrations. They were vibrant, patterned animals that were clearly using color for display. It is highly probable that the larger, non-feathered dinosaurs were also brightly colored, using patches of colorful skin on their frills, sails, or inflatable throat pouches to signal to one another, much like modern lizards and birds do. With all these tools at their disposal, the visual signals of their horns and crests, the auditory signals of their calls, and the vibrant colors of their skin and feathers, we, can begin to imagine the scene. A breeding ground in the late Cretaceous. Male Triceratops, their massive frills flushed with bright, threatening colors, lock horns in a titanic shoving match. A male Parasaurolophus stands tall, inflates a colorful throat sac, and sends a deep, booming call across the floodplain. A male Tyrannosaurus rex, perhaps using the same logic, may have flaunted its size, the health of its skin, and the power of its roar. And what of the female's role in this? Courtship is not a one-way street. The female is the ultimate arbiter, the one who chooses the mate that she deems most fit. A female ceratopsian would have carefully observed the combat between males, choosing the victor. A female hadrosaur would have listened to the chorus of calls, selecting the one with the most impressive resonance. She was an active and crucial participant in this evolutionary play. Once a mate was chosen, the next challenge was the physical act of copulation. This is perhaps the most speculative area of all. For a pair of 2-ton, bipedal hadrosaurs, the mechanics might have been relatively straightforward, perhaps resembling the mating of modern ostriches. But for a pair of 8-ton stegosaurus, with the male facing a gauntlet of lethal tail spikes, or 4 to 50-ton sauropods, the logistics are mind-boggling. The most likely scenario for these large quadrupedal dinosaurs involved the male approaching the female from behind, placing his front legs on her back for support and twisting his tail underneath hers to align their cloacas. It would have been a slow, precarious, and monumental undertaking. A true clash of titans that was the necessary prelude to the creation of the next generation, as the courtship was over. The game had been won. The next stage of the journey, the development and laying of the egg, could now begin. The courtship is over. The high-stakes game of display, ritual, and combat has been won, and a successful mating has occurred. Now the biological imperative shifts from the external world of competition to the internal world of creation. Inside the female dinosaur, a process of profound and ancient biological engineering begins, the formation of the egg. This is the crucial bridge between generations, a self-contained, armored life support system that will carry the genetic legacy of the dinosaurs into the future. By studying the fossilized eggs they left behind, we can open a direct window into this most critical and vulnerable stage of their life cycle. The process began with the fertilization of an ovum deep within the female's reproductive tract. As this fertilized cell traveled down the oviduct, it was gradually encased in layers of albumin, the egg white, and protective membranes. The final and most critical stage was the formation of the shell. Specialized gland, the shell gland, would secrete layers of calcium carbonate around the egg, creating a hard protective outer casing. This entire process is remarkably similar to what happens in modern birds and crocodiles. Another strong confirmation of the power of our phylogenetic bracket. The fossil evidence for this process is subtle but powerful. In 2005, a remarkable fossil was discovered in China. It was the skeleton of a small, bird-like oviraptorosaur. Trapped within its pelvic canal were 2 fully formed, shelled eggs, positioned side by side. This unfortunate individual, nicknamed Mrs. T, died in the very act of egg laying. This incredible fossil was a Rosetta Stone for dinosaur reproduction. It proved for the first time that at least some dinosaurs possessed 2 functional oviducts, like crocodiles. But they only shelled and laid 1 egg from each oviduct at a time. A pattern that is intermediate between crocodiles who lay many eggs from each oviduct at once, and birds who have lost 1 functional oviduct entirely. It was a perfect snapshot of an evolutionary transition. Even more remarkable is the discovery of a specialized type of bone tissue called medullary bone in some dinosaur fossils. Medullary bone is a unique, calcium-rich tissue that female birds grow on the inside surfaces of their bones just before and during the egg-laying season. It serves as a temporary, easily mobilized calcium reservoir that can be quickly drawn upon to form the massive amount of calcium carbonate needed for the eggshells. Finding this same distinctive bone tissue in the fossilized femur of a female Tyrannosaurus rex and a long-necked Allosaurus was a groundbreaking discovery. It provided a direct physiological link between these ancient giants and modern birds. It also gave us, for the first time, a definitive way to identify the sex of a dinosaur fossil. If it has medullary bone, It is an egg-laying female. Once the eggs were formed, the female faced the critical task of finding a suitable location to lay them. The choice of a nesting site was a matter of life and death for her offspring. The site needed to be safe from predators, protected from the elements, and have the correct temperature and humidity to ensure the proper incubation of the eggs. The fossil record shows that dinosaurs, like their modern relatives, were often highly selective about where they built their nurseries. In 1978, paleontologist Jack Horner made a discovery in Montana that would revolutionize our understanding of dinosaur family life. He found not just isolated nests, but a massive colonial nesting ground, a prehistoric metropolis of dinosaur nurseries. The site, which he nicknamed Egg Mountain, contained the nests of a new species of hadrosaur he named Maiasaura, the good mother lizard. The nests were built in shallow, crater-like depressions, spaced roughly 25 feet apart, about the length of an adult Maiasaura. This deliberate spacing suggests that the females returned to the same nesting site year after year, a behavior known as site fidelity. This was not just a collection of nests, it was a community. The eggs themselves are marvels of biological architecture. Fossil dinosaur eggs come in a wide variety of shapes and sizes. The eggs of long-necked sauropods were often large and spherical, like a cantaloupe. The eggs of theropods, like Oviraptor, were typically elongated and laid in complex ring-like patterns. The surface of the eggs was not smooth, but was covered in microscopic pores. These pores were crucial for gas exchange, allowing oxygen to enter the egg and carbon dioxide to escape, enabling the developing embryo to breathe. The number and shape of these pores can tell us about the type of nest the egg was laid in. Eggs with many large pores were likely buried in moist soil or vegetation, where gas exchange was difficult. Eggs with fewer smaller pores were likely laid in more open nests, exposed to the air. The number of eggs in a single nest, a clutch, also varied greatly. A large sauropod might lay a clutch of 20 to 30 large eggs. Maiasaura nest contained a similar number. This reproductive strategy is one of quantity over quality. By laying a large number of eggs, the parents were betting that, even with high rates of predation and failure, at least a few of their offspring would survive to adulthood. This contrasts with the strategy of modern birds, who typically lay a much smaller number of eggs and invest heavily in the care of each one. Once the eggs were laid, the final and most dangerous stage of the process began: incubation. This is the long, vulnerable period during which the embryos must be kept at a stable temperature to develop properly. How did dinosaurs incubate their eggs? Again, we look to their living relatives and the fossil record for clues. Crocodiles typically bury their eggs in a large mound of rotting vegetation. The decomposition of the plant matter generates a steady, natural heat that incubates the eggs. The parent then stands guard over the nest, protecting it from predators. Many paleontologists believe that the giant sauropods and hadrosaurs likely used a similar strategy. Their sheer body size would have made direct brooding, sitting on the eggs, impossible. A 50-ton Argentinosaurus would have instantly crushed its own clutch. Instead, they likely dug shallow pits, laid their eggs, and then covered them with sand or vegetation, relying on the heat of the sun and geothermal activity to do the work of incubation. However, the fossil record from the Gobi Desert tells a more intimate story for some of the smaller theropod dinosaurs. Several remarkable fossils have been discovered of oviraptorosaurs, like Oviraptor and Citipodi, preserved in a lifelike posture, sitting directly on top of their nests of eggs. Their arms were spread out around the clutch, forming a protective cage. This was undeniable, fossilized proof of parental care in the form of direct, bird-like brooding. These dinosaurs were not just laying their eggs and leaving them to fate. They were dedicated, attentive parents using their own body heat, likely enhanced by a coat of insulating feathers, to nurture their developing young. This was the final act of creation. The courtship had led to mating. The mating had led to the formation of the egg. And the egg had been carefully laid and was now being incubated, either by the gentle heat of the earth or the dedicated warmth of a parent's body. Inside each of these stony shells, a miniature dinosaur was growing. A tiny heart was beginning to beat. And a new generation of the rulers of the Mesozoic was preparing to hatch into a world of giants. The cycle of life was about to begin anew. The long, watchful period of incubation is drawing to a close. Inside the protective confines of the eggshell, a miniature dinosaur. A fully formed but fragile replica of its colossal parents is ready to emerge. For weeks or months, it has been nourished by the rich yolk sac, its tiny lungs developing, its bones hardening, its muscles gaining strength. Now, it must perform the first and most critical act of its independent life. It must break free. The story of hatching and the perilous journey of the dinosaurian young provides our final, poignant glimpse into the reproductive cycle of these magnificent creatures. The process of hatching was an arduous struggle. The hatchling, curled tightly within the egg, was equipped with a specialized tool for this very purpose. Like modern birds and crocodiles, it likely possessed an egg tooth, a small, sharp, temporary projection on the tip of its snout. Using this tool and driven by the primal instinct to escape, the hatchling would begin to push and scrape against the inner wall of its shell. This process, called pipping, would create a series of small cracks, with a final coordinated effort of its neck and leg muscles. The hatchling would break a larger opening and wriggle its way out into a new and dangerous world. The fossil evidence for this first crucial moment is exceptionally rare, but it does exist. At the Egg Mountain site in Montana, Jack Horner's team found the remains of baby Maiasaura that were still inside their eggs, as well as the shattered fragments of hatched eggs. The way the eggs were broken with the tops neatly popped off suggests a controlled, deliberate hatching process, not the random smashing that would result from a predator's attack. What the world looked like to a freshly hatched dinosaur depended entirely on its species. Paleontologists classify young animals into two broad categories: precocial and altricial. Precocial young are born in an advanced state of development. They are mobile, alert, and can feed themselves almost immediately after hatching. A modern example is a baby duckling, which can walk and swim within hours of leaving the egg. Altricial young, on the other hand, are born helpless. They are often naked, blind, and completely dependent on their parents for food, warmth, and protection. A baby robin is a classic altricial animal. Where did dinosaur hatchlings fall on this spectrum? The evidence suggests that, like so much of their biology, it was diverse. The young of the giant sauropods were likely highly precocial. A baby Argentinosaurus was already the size of a large dog at hatching, but it was a mere fraction of its parents' 90-ton bulk. It would have been impossible for the colossal adults to provide direct care to their tiny offspring without the risk of accidentally crushing them. The most likely scenario is that sauropod hatchlings emerged from their buried nests in large groups and were on their own from day one. Their survival strategy was one of rapid growth. They would seek the cover of dense forests, away from the giant predators that roamed the open plains and eat voraciously, growing at an incredible rate to escape the window of vulnerability as quickly as possible. The story for the Maiasaura at Egg Mountain, however, was dramatically different. When Horner's team examined the fossilized skeletons of the hatchlings found within the nests, they made a critical observation. The ends of the baby's leg bones were not fully ossified. They were still soft cartilage. This meant that the baby Maiasaura were not capable of walking or leaving the nest immediately after hatching. They were physically unable to fend for themselves. This was the first strong evidence for altricial, helpless young in any dinosaur. This discovery had profound implications for their family life. If the babies couldn't leave the nest, then the parents must have been bringing food to them. The presence of chewed-up plant fragments in the nesting area, along with the worn-down teeth of the hatchlings, confirmed this hypothesis. The Maiasaura parents were practicing dedicated, extended parental care. They were guarding their nests, feeding their helpless young, and likely protecting them for a significant period after they hatched. The colonial nesting ground was not just a place to lay eggs. It was a true community, a prehistoric daycare where the next generation was nurtured and protected. This intimate, bird-like parental care was a far cry from the reptilian model of lay them and leave them. This model of dedicated parenting is even more strongly supported for the brooding theropods like Psittacipodi. The adult, found fossilized on its nest, was not just incubating the eggs, it was guarding a nursery. It was a parent prepared to die to protect its young, a level of commitment that speaks to a powerful, instinctual bond. The young of these theropods were likely also altricial, relying on their parents for food and protection in the dangerous early stages of life. This period of infancy was, without a doubt, the most perilous time in a dinosaur's life. The world was filled with predators of all sizes, many of which may have specialized in raiding nests and preying on vulnerable hatchlings. Small mammals, lizards, snakes, and other smaller dinosaurs would have posed a constant threat. Even for the species that practiced parental care, a moment of inattention from a parent could mean disaster. The mortality rate for young dinosaurs was likely incredibly high. For every individual that survived to adulthood, dozens or even hundreds of its siblings may have perished. But for those that did survive through the luck of the draw, the strength of their parents, or their own innate resilience, the journey to adulthood was a story of spectacular growth and transformation. From a tiny, vulnerable hatchling, they would embark on a decades-long journey to become the colossal, magnificent rulers of their world. The story of dinosaur reproduction is a testament to the power of scientific deduction. From a few scattered bones, broken eggshells, and the biology of their living relatives, we have pieced together a vibrant and intimate portrait of their private lives. You can now envision the spectacular courtship displays, the monumental act of mating, the physiological marvel of egg formation, and the tender, dedicated care of a parent for its young. It is a story that transforms these ancient creatures from static museum monsters into dynamic, living beings driven by the same fundamental impulse that drives all life on Earth: the profound, unyielding imperative to create the next generation and continue the great, unbroken chain of existence.